the cloud. All right, so I'm gonna stop recording on my local side and make sure I'm using the right mic here. Okay, that is correct. Okay. And this time I cannot hear anything from the other side because I forgot to bring my Bluetooth. So for the person who is online, if you need to ask questions, you will probably have to type it in the chat of Zoom. And I need to open that window first. Okay, there we go. All right, so I'm gonna type something. There we go. Okay. All right. So the first part of the lecture is actually recorded, so you kind of have to catch up with that part a little bit later. All right. So what was the question again? Venn diagram. Okay, picture diagram. Okay. So let me see what I can do here. It's just not auto-rotating. And the control of rotation. Oh, okay. So I can do the, there we go. Okay. Now I can use this. Hook it up to here. And display on the screen. Give me a second. There we go. All right. So instead of a Venn diagram, the way a function is displayed. All right. So do we have any questions back there? Yes? Any questions for me? Okay. All right. So we are going to use the same example. Okay. So we're going to take a look at this particular example here. So let me slide the editor to the side a little bit so we can see more on the tablet. So the way we display that is we have A, B, C, and then we have 1, 2, 3 on the other side. So typically, some people use this notation to say A maps to 2, B maps to 1, and then C maps to 3. So does that answer the question of how to use a diagram to display the function, which one is the domain, which one is the codomain, and how things map? Yep. Okay. Okay. So if you have something like this, 1, 2, 3, 4, and this is a different function. So once again, ABC is the domain, 1, 2, 3, 4 is the codomain this time. Okay. So now if you map A to 1, C to 2, and then B to 4, it is still an injection, but it's not a surjection anymore because element 3 of the codomain is not mapped to. So this one is an injection, but not a surjection. Is that okay? And then if you have, once again, ABC, and then the other side can be just AB. Oops, not AB. We'll make it 1, 2. And everything maps to 1. Okay. Now we have it's neither an injection nor a surjection. Okay, I'll write it here. This is a bijection. This is injection only. And this is a surjection. Nope, nope. This one is not a surjection nor an injection. So it's neither. So we need one more example where it is a surjection but not an injection. That's easy. Now we have something that is a surjection only. All right, so does that help? Yes. It is, well, it is displayed. It's just, I have to slide the editor a little bit over. There we go. Yep.
So in the event where you wanted to prove the function is a bijective function,
Mm-hmm.
Is there any scenario in which the easiest way to do that would be to prove that first of that function is bijective?
Okay, so you can prove it through many ways. You can prove if you want to prove the injective part, then what you need to do is to show that for any two different values from the domain, they have to map to two different values in the codomain. You can prove that. If you want to prove surjection, then you have to prove, no matter what value is in the codomain, something from the domain has to map to it. So those are two separate, steps of proving.
Yeah.
Yep.
Isn't inverse just flipping the whole sets around and just making sure they have to?
The inverse means you reverse all the arrows. The question is, you can reverse all the arrows for every single case. The question is, once you reverse the arrows, do you still have a function?
I mean, wouldn't it be the same as all you're doing is reverse
Wouldn't be the same as what?
as mapping each element to this? Like if A, B, C are mapped to three,
Mm-hmm.
you inverse it and make it two.
It is not the same thing. It would be the inverse of the original thing. But you don't get a function for the other ones, because if you do not start with a bijection, you reverse the direction of all the arrows, then you don't have a function. It still looks like a map, but it's not a function.
Why is it a
Okay, so let me answer that question. Can you hold on to that question?
Yeah, it has to be.
Okay, go ahead.
So, ABC 1, 2, that's just a function that we reverse it. Since 1 is the domain, would that mean that it's not a function?
Well, let's work with the second one first, and then we'll work with the third one, okay? So we'll reverse all the arrows. So I'm basically looking at this particular map and just reverse all the arrows, okay? So B maps to 4, so now 4 maps to B, and C maps to 2, and now 2 maps to C, okay? So now the question is, why is this not a function? So I'm gonna not even a function. And why is that? Okay, so how do we answer a question like that? Okay, let's go through the thought process of, how do we answer that question other than asking tech about it. It's not because I'm impatient. I may be impatient, but it's not because of that. But it's because you should be able to answer that question. Why is the thing in the rectangle not even a function? So what do you start with? Start definitions, okay? And what is the definition of a function? What are the two requirements? One is the mapping has to be a subset of the Cartesian product. Well, this is still, this is still a subset of the Cartesian product, except this time you're looking at the Cartesian product of the set 1, 2, 3, 4 with ABC instead of the other way around. So the subset requirement is fine. What is the second requirement in order for a function to be in order for a subset of the Cartesian product to be a function? Yes. One and only one. Yes, very good. So now we look at this and go, is that requirement met? Are the elements 1, 2, 3, and 4 from the new domain, is each one mapping to one and only one thing in the codomain? The answer is, why are you guys nodding your head? Do you not see that C is not mapping to anything? 3. Oh, sorry, 3. Okay, sorry. My bad. But do you not see that 3 is not mapping to anything? There's no arrow coming out of 3. So that means we have an element in the domain or its proposed domain that is not mapping to anything in the codomain. That requirement has failed. Is that okay? So that's how we answer the question. Go back to the definition, apply the definition, and apply the requirements to whatever is given to you, evaluate it, then you can find out whether it is still a function or not. Yes. So we want to now move on to the third example, okay? So with the third example, we have 1, 2 as the domain, and then A, B, C as the codomain. Everything mapped to A1. So now we map 1 back to everything else. So now the question is, what is this? Well, once again, this is not even a function, but for a different reason. Well, okay, I shouldn't say different reason. There are multiple reasons why this is not even a function, because when you look at 2, it does not map to anything. But when you look at 1, it maps to, guess what? 3 different things. If we want this to be a function, each element of the domain can only map to one and only one element in the codomain. So not only did this fail the test, it failed the test miserably, as opposed to just failing the test. Yep.
So if there's more elements of the domain than the codomain, it's automatically not a function.
If there are more elements in the domain than there are elements in the codomain, nope, that is not the case. we already look at this one. This is a function where there are more elements in the domain. Okay, I need to use the mouse pointer.
More elements of the codomain than in
This is also a function. It's just not surjective. You said there are more elements in the codomain than there are elements in the domain.
Yeah, so for the example that number 6.
This one?
Yes.
That's not a function.
Yeah, I know.
Yeah.
But what I'm saying here is that no matter if there are more elements in the domain than the codomain, it must map to each element in the domain must map to one and only one element in the codomain, right? So if there are more elements in the codomain, the domain, then it can still be true.
It can still be a function. It just cannot be a surjection. If there are more elements in the codomain than there are elements in the domain, then you cannot have all the elements in the codomain mapped to, and therefore it is not possible to be a surjection. But it can still be a function.
But as part of the function, each element must map to one and only one element.
But it doesn't specify which one. Yep.
But is it possible to make a message qualifications diagram? For example, same as in the numbers, we have top, the parent is all real numbers, then we have the rational numbers, and all rational numbers are real numbers, but not all real numbers are rational. You have the same thing for.
We'll work on something like that when we get to Aleph No. In fact, it'll be more fun when we get to Aleph No. Yep.
I don't know if this is something, but you give an example of a proof of a bijective function where it's easier to prove that the function is bijective rather than
I think when we get to Aleph No, we'll get something like that, but not exactly super easy, but we'll get to that. Yep. Any other questions? Okay. So I'll leave that one up in the background when I go back to the text here. So if we were to get back to the sorting example, once we have the notation of a bijection, then we can define what sorting is, because we need a bijection to map the index of the array after sorting to the array of original values before the sort. So that has to be a bijection. In other words, every value that you start off with in the array has to map to one and only one unique item in the array after it is sorted. Now, can multiple elements in the array have the same value? Yes, sure, no problem. I'm talking about positioning in the array. Is that okay? Just in general? Yep. Huh? Position, like the index of an element in an array. Okay, so let's go back to that one, and I'll just kind of add one more thing so that you can relate back to it. So it is here, and we talk about all the way down to here, and we say even with the notion of a function, this is not sufficient because the function itself can be not a bijection in this case. In other words, f of I maps everything to 0. So if f of I maps everything to 0, so that means I can basically copy the original item in as the first element of the entire array to the rest of the array, and then this requirement will be met. Does that make sense? Because f of whatever is just 0. So that means I take the first element of the original array as the input, I copy that element throughout the entire array, and this requirement will be met. It would also meet the requirement of every element is less than or equal to the one next to it, because they're all the same. Is that okay? So, but now that we understand what is bijection, now we can say, okay, but wait, f is not just any function. It has to be a bijection. So once we add the requirement that f has to be a bijection with this, and also the earlier requirement, which is every element has to be less than or equal to the one that is following it, which is this one here, by looking at this, and also adding the fact that f has to be a bijection, now we can mathematically define what is the correct outcome of a sorting algorithm. It takes this much work to describe what it entails to sort an array if we are to use mathematical notations. Okay? So why do we have to be doing this type of thing? Why are we splitting hair? Why don't we just say sort? Okay, because everybody knows what sort is. Do you think you'll be hired to write a sorting algorithm? No. Hard no. Do you know that Meta has just fired more than 3,000 employees over the weekend? Many of which, according to what I have read, received a stellar review. So it's not like they're underperforming, but they were getting fired anyway. Okay, I know you guys do not believe me, and that's the right attitude in my classes. I would not have believed myself if I were a student in my own class. It's always good to ask questions and ask for, okay, show it to me. Okay, so we can just look up Meta fired employees. Okay, that should be enough to find something here. Fired Meta workers say they have records of good, solid track record. And it says thousands here. It's actually more than 3,000 employees. So once again, do you think you'll be hired to write a sorting algorithm? And I know somebody's going to say, but I'm smarter than everybody else. I can write a sorting algorithm that beats the n log n time complexity. And I can say, yeah, but mathematically it is not possible. You cannot write a sorting algorithm that is faster than n log n. Yes.
The guy who Tim's one Python is also fired.
For what reason? Oh, okay. So, okay. Well, that's a different reason. Uh-huh. So that's the kind of competition and that's the kind of atmosphere that you guys are going into in about 2 years or so, okay? Because you graduate from here and then you have 2 more years at a 4-year university. Then you graduate with a bachelor's degree and then you'll be looking for jobs. And guess what these 3,000 people will be doing? They'll be competing for the same jobs with job experience, with a resume that says, I have been working at Meta for X many years. That's the kind of situation that you're running into right now. Okay. Yeah. I know it doesn't sound very encouraging, but I'm not here to be encouraging. I'm here to tell you stuff that hopefully is true. So now you have to ask yourself this question. It's like, what am I going to do, okay, in this scenario? Okay. Um, there are a few options, okay? There are actually a few options. One option is I'm going to switch to diesel technology. And you would think that I'm kidding, but I'm actually not kidding, okay? Because in diesel technology or automotive technology or funeral services, okay, when do you think AI will take over the jobs in funeral services? Not anytime soon, okay? Now, if you are, an administrator, with funeral services, you can still use AI, okay? You can still use AI to help you plan the events and whatnot, okay? But they still need a person to be coordinating, okay, to be comforting the relatives of the deceased and so on and so forth. And someone has to push the button of the incinerator, right? So yes, that would be that job that is pretty hard to replace with AI. Okay, AI can help with that job, but not to replace it. Anything that only involves intellectual work are the easiest to be replaced. In terms of medical science, a surgeon, maybe in time they can be replaced. Okay, when robotics get to the point where the AI can perform surgery, well, maybe they can be replaced. The first ones to be replaced are the radiologists, because what do they do? What is a radiologist? They look at images. Okay, generally speaking, images or 3D images, because they can do a CAT scan and now it's a 3D thing. Well, guess what? There are many cases now where the AI can identify something where the human cannot. And then later on, when they opened up the patient, they confirmed that the AI was actually correct. So, so we are moving in that kind of direction. Okay. So I'm not kidding when I say, consider other career options, especially if computer science classes is a chore and is painful to you. Okay. Yes.
What about government IT or government cybersecurity?
You can try that too, okay? But I'm not sure, I know you're smart, but you're probably not the first person to think of this plan. So that means, the competition to get into IT for any government job is also going to be competitive. People are just trying to find exits everywhere. Most people go to graduate school, okay, right after they graduate, like last year with a bachelor's degree, they spend half a year not being able to find a job in computer science, in software engineering. So many of those people are now going for graduate school. But in 2 years' time, what do you think is going to happen? They're all going to graduate with a master's degree in computer science. So now you're getting into the same situation again, okay? Because now you just have a massive amount of people with a master's degree in computer science. Do you think there'll be more jobs in computer science? Maybe, maybe not. Okay, I really do not know. Okay, which way it's gonna go. Yep. Yep.
So there's different options to be in computer science. Just because everyone's looking for a job doesn't mean you can't make your own company or make your own business.
What are you gonna sell?
So, so websites.
And do you know what your competition is gonna be?
Like Google can be competition, Facebook, but there's always an option out there to make money because the market's too big. Like if you actually do research on the market, you can see how much money.
But where is that money going to? What kind of people? I can tell you the people what the people are. Okay, who was present in the inauguration of President Trump? Elon Musk and Mark Zuckerberg and
Everyone but the NVIDIA C.
exactly. But they are billionaires already. The technology, I think, is enabling the billionaires to become even more billionaire. And for the rest of us, it's getting harder and harder to find a job that can make a living.
Job. But everyone must get a job. You don't have to get a job.
I can write an app too, but who's going to buy my app?
There's probably some,
Yes.
I'm not like a big fan of Rumble, but
Mm-hmm.
I'm pretty sure, I mean, if you do this, Facebook, if you do this, someone's gonna buy it. Somebody's gonna make it somehow.
Okay. Have you tried to use ChatGPT to make an app?
I've used it for this program.
Give it a try. Yep. Yes.
There was a whole chart thing that was someone did out to show maps of airports,
Mm-hmm.
and they tore the guy apart. They said like Google Maps does it for free. Why would anyone buy your product? So, like, why would anyone buy your?
If it's if it is not for guardrails, okay, even scam artists will be out of a job because AI can out scam scammers. It's only because of the guardrail that it cannot, answer your prompt with, "How do I make a scam doing this?" Yes.
Verification will always be required though.
Yes. So verification, but verification is hard, okay? Because verification, formal verification, which we'll be talking about too. So we'll get to propositional calculus and also predicate calculus. Both of those are basically baby steps into formal verification, which is using mathematics to prove the correctness of a program. So that is needed, okay, because of cybersecurity. And there will be jobs, okay? And those are difficult problems for a computer to solve because it involves rigorous application of logic. I know it sounds really weird, okay, but the AIs cannot. The one thing it cannot really outdo people, is mathematical proofs, using rigorous logic. So if you're good at that sort of thing, which means you're going to find this class, to be way too easy. You're asleep most of the time, and you go like, I know this stuff already, then you probably can get into that kind of a job. Yes.
I just thought of like at the rate that AI is advancing at,
Mm-hmm.
isn't it just gonna like this problem of people's jobs being replaced by AI?
Mm-hmm.
I feel like it's probably gonna fold back over and go around the other way. What I mean by that is like eventually, what if AI gets to the point where the people who are like selling these programs and making them with AI can't sell them anymore because the average consumer can just AI to make it sell.
Yep. So then what's going to happen? So what kind of people will start to make money again?
I guess whoever has the rights to the AI.
If you have a guitar, you open the guitar case like right outside of this building, and you start playing. You'll be making money because there'll be people who want to go back to the basics. They want to listen to a person who, actually playing the music, instead of just listening to the AI, AI generated music, and everything that is not human generated. So we're getting back to that. Okay, so don't, sell your guitars just yet. You might find it useful, or your flutes, or your violins, or your pianos, or your piccolos. I hate piccolos, but yes.
What I'm getting is like a lot of it depends on your creativity.
Yes, a lot depends on your creativity. But what is creativity? Well, curiosity correlates with creativity. But what exactly is creativity? Why do you think AI does not have creativity? It is not just pattern recognition. It does, a little more than that. Okay. Yep.
This is gonna be a little bit philosophical, but free will, I guess.
It is philosophical because we don't even know whether that is true or not. Do you have free will? Yes. But don't we do that too?
Well, we can create something original.
What do you mean by original?
I could put a paint on the wall and say, I'll sell it for $7 million.
But AI can do that too. A robot can throw, a bucket of paint, to the wall and go like, "This is art. Look how creative it is." Adding noise is easy, right? So the bottom line is, this is just me personally thinking about it. is if you want, to get a job, okay, in 2 years or so, the fundamentals are important. Okay, in other words, knowing the notations, how. Okay, let's go back to the slide that we were on. Okay, something as simple as this. Just you're trying to specify what it means to have a sorting function. Okay, what is the outcome of a sorting function, and how do we mathematically describe it? I think that's going to be important. Okay, because the actual steps to prove it may not be undoable using a machine, but specifying what the algorithm is supposed to do can be the difficult part. Okay, to quote Sam Altman again, okay, the key is to know what questions to ask. Okay, and what if the question is just like, I'm just going to go ask tech? Okay, is that knowing what question to ask? So kind of chew on this a little bit. Okay, I know a lot of this is um, it's it's difficult to sink in, but it is important nonetheless. Okay, all right. We'll go into Aleph No at this point because we're transitioning to Aleph No. And the whole point of Aleph No is, by definition, the Aleph No, this particular symbol here, is the cardinality of the set of natural numbers. Okay, so by definition, Aleph No is the cardinality of the set of natural numbers. Are we good with that? Are we good with the definition of Aleph No? Okay, which is here. That's the definition. So what is the significance of that? The significance of that is I can show, okay, the cardinality of the set of integers is the same as the cardinality of the set of natural numbers. Okay, so I'm going to switch to the tablet. Okay, so what I'm trying to say is the cardinality of the set of integers is the same as the cardinality of the set of natural numbers. Okay, that's my claim. Okay, so I would prove it. I would need steps to prove that. You look at this and go like, but that does not make sense. Okay, it does not make sense because we can have very concrete observations and go like, -1 is an element of the set of natural integers. Yes, this is true. -1 is an element of the set of natural numbers. It's false. In other words, there are quote unquote more elements in the set of integers than there are elements in the set of natural numbers. Does that make sense to you? Yes. So that's what we're going to do. Okay, that's the key to the understanding of the equivalency of cardinality. So now you can even say this. Okay, this is actually true. The set of all natural number is a proper subset of the set of all integers. It makes sense, right? Because everything that is a natural number has to be an integer as well. But there are integers that are not natural numbers, like -5. Is that okay? So given these are true, okay, given this is true, um, -1 can only be found in the set of integers, but not in the set of natural numbers. This equality sounds really dubious, okay? But you cannot compare infinity to infinity, okay? So if you think about the actual number of elements in the set of integers as opposed to the actual number of elements in the set of the number of elements in the set of natural numbers, it's infinite. You cannot compare that. So the equivalency is established by a bijective function. Okay, so we now say, give me any set. Okay, give me any set description. So I can now say the cardinality of set X is the same as Aleph No. Again, I have to always remind myself how to write Aleph No. Okay, so this is, am I, okay. So I know it's a very poor imitation penmanship, okay, but just fine. because it's the same thing, right? If and only if there exists a bijective function f that maps from x to the set of natural numbers. The direction doesn't matter, okay? Because if this is a bijection, then it can go from here to here. It can go back from the set of natural number to x, because with a bijection, it naturally has an inverse, and the inverse is also a bijection. So it doesn't really matter which way it goes. Okay. So now you go like, okay, since tag claims that the cardinality of the set of integers is the same as the cardinality of the set of natural numbers, that means such a function must exist. Okay, so I'll give you the function. So, so when we look at this f here, okay, this f is going to map from integers, okay, to natural numbers. And f is defined further like this. F of x is x mod 2. Nope, I take it back. Don't copy anything. In fact, there's no need to copy anything because everything that I'm talking about right now is in the notes. So what you need to write down are your thoughts, your understanding of the concepts. So this is x is less than 0. That's it. So if x is less than 0, let's do a 2 times x plus 1. Otherwise, we'll just do a 2x. That's how I define function f. And does anyone need me to explain what is the question mark and the colon? I know which one of you have taken my CISP 310? Yes. You want me to explain what that is? Okay, yes. So this is a ternary operator, okay? If this, then this, else this. Okay, it's a if then else in a single expression. That's what it is. So I want you guys to kind of go through the whole process. Okay, so tell me what is f of 0. Just apply the definition and tell me what is f of 0. F of 0 is, okay, first of all, okay, let's go step by step. Is 0 less than 0? No, 0 is not less than 0. So we go to the else. What is 2 times 0? 0. Very good. What is f of -1? So f of -1 is, okay, so evaluate x first, okay? Is -1 less than 0?
Yeah.
True. So what is -2 times -1? 2, and then we have a +1. Okay, I messed up here. I messed up because this is supposed to be a -1, not a +1. It makes a minor difference, but nonetheless, it is an important difference. So this is supposed to be a -1. There we go. Okay, so once again, what is f of -1? 2 minus 1 is 1. Okay, very good. What is f of 1? So is 1 less than 0? Nope. What is 2 times 1? 2. Okay. And I think once we get to the next one, you guys will go like, oh, okay, I see how that goes. What is f of -2? -2 is less than 0? True. -2 times -2 is 4. 4 minus 1 is 3. Okay. And then we'll do one more. That's 4. Do you see the pattern? Okay. So are you convinced that this is a bijection? How do you prove this is a bi? Okay, first of all, how do you prove that this is at least an injection? Mhm. No, that's just a function. We need uniqueness. Okay. So you have to say, if I give you two different values, two different integers, x and y, f of x and f of y are guaranteed to be different. Okay, so how do we prove that? Well, there are two cases. One is when both x and y are negative, and then the other one is when both x and y are non-negative. So if they're both negative, then only this one applies, okay? And because x and y, the two values are different, so this expression will give you two different values. If they're both non-negative, then only we are looking at two times two different values. So the two times of the product of two and the two different values are different, guaranteed. That's arithmetic, right? So that's kind of a very informal way to prove that this function is at least injective. So now how do we show that this function is also surjective? In other words, if I give you a natural number, there has to be an integer that maps to it. In other words, can we reverse the process? Well, let's see. Okay, so let's just say that we are looking at 47. Okay, so 47 is f of x. I'm asking you, what is x in order to make f of x 47? How would you approach that problem? Hmm? What is your thought process? Aha, how do you know it's negative? All the, yes, all the odd natural numbers are mapped from negative integers. Very good. And that's because of the logic here. Okay, the only time you end up with a even number is when x is non-negative because of this condition. So the only time you end up with an odd number is negative 2x minus 1. That's the only time you can end up with an odd number. So 47 is an odd number. Okay, very good. Then what do? We have to undo this thing here, right? So now we have to say, okay, so now we know negative 2 times x minus 1 is 47. Can we solve x from this? I think so, right? It's just algebra. So we'll go ahead and work out the algebra part here. This is 46 is negative 2x. X is 46 divided by negative 2, which is negative 23. Done. So now that we know how to work out a specific value, can we generalize and go like, oh, okay, I can kind of generalize this whole thing. Yep. Say again. You are correct. As I said, I would have been a B student in my own class. This is 40. Oh, no, that's not what fix. Mm-hmm. Well, so you reverse the yeah. It will still work. It may be not the same as what the notes is saying, but it's the same idea. It's just you have to reverse the then versus the else expressions. Mhm. All right, but let me fix this. Okay, this is not right. This is not right. It's not right. 48, 48, 24. There we go. But the idea is, yes, there is a way to reverse it. What if x is a even number? Excuse me. What if f of x is an even number? Let's say 100 even. Okay. So I want to ask what is x in this case? This one is easy, right? Because the only time you end up with an even number is when x is less than 0 is false. Okay. But to reverse it, you just go like if 2x is 100, which you cannot see, then x is going to be 50. So x is 50 in this case. Okay. So what if I need you to describe the general method instead of saying, okay, if you give me a specific value, I know how to reverse it. So if I need you to tell me, generally speaking, if I give you a particular natural number and I need you to figure out what integer maps to that specific natural number, what would be the logic? sounds like we have a decision to make first, okay, which is
Well, you're always gonna divide by
nope. Well, okay, there's always a divide by two. The question is, when do you do the division by two? So the first thing we need to do is to ask, do we have an even number or do we have an odd number? Right? Because if it's an odd number, we have to apply one particular method. If it's an even number, we apply the other method. Does that make sense? So if it is even number, okay, because when x mod 2 is a 0, it's an even number, then it's easy peasy, okay? This is the case where yeah, we just divide it by 2. Otherwise, we have an odd number. If it's an odd number, then we have to add 1 to x first and then divide the whole thing by -2. So this becomes x plus 1, the whole thing divided by -2. So we just created a function that is a bijection between the set of all natural numbers and the set of all integers. Is that okay? But because such a function exists, now is this the only function to map, uh, is this the only bijection that maps between the set of integers and the set of natural numbers? The answer is unlikely, okay? There may be many other ways to do the same thing. All I need is at least one function like this, and I found it. So that means I can now establish the equivalency between the cardinality of the set of integers and the set of natural numbers. Okay, so I can say because such a bijection exists, the cardinality of integers is now the same as the cardinality of natural numbers. Is that okay? But it is a little bit tricky to look at because even though one, the set of natural number is really a proper subset of the set of integers, and yet we have established that their cardinalities are the same. So, so you kind of have to not use the intuitive way of looking at cardinality and equivalence, but use the definition of can we find a bijection between these two sets? Is that okay? So now we move on to something that's even more fun. So now we are looking at the set as the cardinality, as the Cartesian product of a natural number times natural number. So now we look at this, and then we look at this, and then we say, do they have the same cardinality or not? What do you think? One is a number line, and the other one is a two-dimensional space. So at least with integers versus natural number, they are both just a line, right? One is a line that starts at a certain place and it extends, in a certain direction. The other one has no starting point. It extends on both sides, and we can establish that they have the same cardinality. This time it's even more fun because now we go like one is just one dimensional, it's a line. The other one is a space, it's a two-dimensional space. Yes.
technically you could keep number line two-dimensional by just taking instead of the y value for every.
But that's not two-dimensional because your y-axis is not going infinitely. So in this case, it is because we are looking. Mhm. But if it's a 0, then you're not using the entire space. This one has the entire space. So I need a bijection. I need some kind of a function. We call it g, so that it is mapping the Cartesian product of natural number and natural number to the set of just natural number. And we want g to be a bijection. So how do we make that happen? If you have read the notes ahead of time, obviously this is going to be a very boring part of the lecture because it's actually really simple, okay? It is the way you lay tiles in a room. Okay, so you have a two-dimensional space, okay, because it's a natural number. So it goes like 0, 1, 2, 3, 0, 1, 2, 3, and so on. So I'm just making myself kind of like a grid system here. Okay, that should be enough to illustrate the way to do it. You ask anyone who knows how to lay tiles professionally, they go like, oh, that's easy. You start with the corner. This is where you put 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. Okay? You just have a room that is infinitely large. But the question is this a way to map every tile to a natural number? And is it bijective? So let's try to answer those two questions, okay? If I have two different tiles, are they guaranteed to have two different natural numbers on it, according to the scheme of how we fill up the numbers? The answer is yes, okay? Because from the algorithm perspective, every time we assign a value to a particular tile, we increment, quote unquote, increment the counter before we move on. So that means it's from the algorithm perspective, it's not possible to assign the same natural number to two different tiles. Is that okay? Which is also to say, if you give me two different tiles, different locations, they are guaranteed to have two different natural numbers. It is injective. Next question is, yes, go ahead.
I was just gonna say, it'd be helpful to to visualize the mapping to say that the output of the left-hand side of the equation is a two tuple, and the output of the right-hand side of the equation is a two tuple. If you were to imagine that.
Okay, so in this case, according to the way it is done here, the G value of 2, 1, okay, 2, 1, 2, 1 is this is 2, which is this is the X and this is the Y. So if we go from 2 and 1, it is a 7. So that's basically what it is. The domain is two-dimensional. The range or the codomain is one-dimensional. Okay? But now let me go back to okay, go ahead. I do not know. All right, so the next question is it surjective? In other words, using this particular way, if I give you a specific natural number, it has to be on a tile. Can that be guaranteed? Every natural number has a tile in a two-dimensional space where it is painted on. Okay, well, it kind of makes sense, right? Because this space, this keeps going on and on and on and on. So that means if you give me a natural number, it's just a matter of time before I can find out which tile has that number on it. Does that make sense? Just intuitively, this is not a formal proof. Yes? Okay. So that makes G injective and surjective, which means it is a bijective. If it is bijective or if it is a bijection, that means I can now establish the equality here. I can now say, yep, they are indeed the same. So I can now erase the question mark because I have just proven that the two-dimensional space of a natural number times natural number, which is also, by the way, how you name pixels on the screen. Okay, it has the same cardinality as just the set of all natural numbers. Isn't that fun? I just folded a two-dimensional space into one. Then what about three-dimensional, four-dimensional, and so on? What do you think? So now we're looking at, why is it not writing? Oh, because I'm using the wrong tool. What about this? Uh-huh. What about this? Can we find a function h that can do this mapping? Well, if I can fold 2 to 1, I can do this because all I need to do is to do something like this, okay? So h of x, y, z can now be defined one of the many ways, okay? Not the only way, but one of the many ways is to say, let's take the g of x, y, and then plus the z over here. I'm first mapping x, y in folding that two-dimensional space into one. Now I have two dimensions, and then I fold that one into one. I can nest the application of function g, and then I can fold any limited or known dimensional space into one dimensional. So from that perspective, this function is kind of interesting. When I wrote my notes here, I did not know there's a name for this one. There's actually a name. It is called Cantor's mapping function, I think. Okay, I have to look it up to be sure. So Cantor's map. Pairing function, not mapping. There we go. It's Cantor's pairing function. There we go. All right, we still have about 2 more minutes. So over the long weekend, because Monday is a holiday, so I will see you guys again on Wednesday. So over the long weekend, you might want to read the notes. You should always read the notes, but this one is kind of interesting because it shows you the derivation of how I derived the whole thing. In other words, I made an observation, and then I went through a bunch of math stuff here, and then eventually I came up with the closed form of the g function. So the g function was derived here. So this is the g function, but since we know that g is a bijection, so there has to be an inverse function. So I also go through a bunch of math stuff, math related reasoning to come up with g inverse, which is all the way down here. So this is g inverse. So now the question is, which part is important? Okay, you have to think about it a little bit. Okay, is it just the fact that I know how g is defined and how g inverse is defined that is important, or is it I know how to derive it that is important? Now, if you have not read my notes yet, okay, you can try to do it by yourself. Okay, don't use ChatGPT, don't Google it. Okay, just knowing how, generally speaking, how g works, try to derive the closed form of g. And then from that, try to derive g inverse. Okay. And I found that my proof, that is actually quoted here, I did everything independently. I did not look it up. Okay. And then later on, I found the proof by Cantor. It was identical. So it's a good feeling. Okay. It's not a good feeling that I did not do a whole bunch of research and redo some work. I'm famous for redoing things, reinventing the wheel every single time. But it is also good to know that I can do it. Okay. So I think that is important in this class. Now, we can disagree, whether rigorous math is actually important for your future career, whether you can get a job or not. Okay. But in this class, that is important. That's my focus in this class. Yes, go ahead.
So this one, the set of all real numbers is countably in, or uncountably infinite is because between each integer in the set of all real numbers, there is a countably infinite.
Uncountably many.
Yeah, okay.
Yep. So that's why the cardinality of real number as a set is known as aleph 1. Okay. Because it is another level of infinite.
Right.
Yeah. That is not mappable to natural numbers. Yep.
Last night, and then it was just showing up as a 0 this morning. I just wanted to make sure that
The set.
the set notation just or not set notation, function as sets assignment.
Oh, that one I think I have to grade.
Okay.
Yeah, because I think those are all open-ended questions. So I think when one student said everything was a 0 or not known, it's because I have to grade it.
Okay.
Yep. And which assignment is due today?
It was the function, it was just the functions and sets, the one where it's just you looking at
Oh, that's the
annotation.
before, the one before. Okay,
Set
all right. So
notation.
I was talking about the wrong assignment.
Oh, okay. Annotation.
Okay.
Is there a way that I could see if you actually like got the assignment and it was just like something?
You should be able to go in and see how you answered it. If you can see how you answered it, I got it.
I can't see any of that.
Oh, you cannot? Oh, okay. Well, I can't show it here because
Okay.
not with other students
Yeah,
here.
yeah.
So for your own privacy, I cannot show it here. Did
I
you send me
can
an email?
compare. I
You
can
did?
send you. Yeah, I can send you.
Okay. Then I can confirm whether I got it or not.
Okay.
Yep.
Question. So you were going over how to actually define like the surjective injection to show it's bijective. So that's, well, we can just go over that and see how it turns to bijective. And then there's like a formula and more notes on there.
So the notes here is about more about the derivation than the so this part, okay, so everything, okay, let me go back to the original Zoom. So it goes through a whole bunch of math stuff, okay, based on observation of how the G function behaves. So I basically look at the pattern and then come to the conclusion, eventually derive the actual closed form of the G function.
Gotcha. I was talking about before the G function. I was thinking
Mhm.
going back and looking at how injective and subjective actually
Oh, okay.
bijective, because I think that's important too, right?
Yes.
Okay.
Yep.
So can you check if this is correct? Like, this is the,
Yes. So bijection is the intersection of injection and surjection.
okay,
Yes.
so function, all elements in domain must map to one.
One and only one. Every element maps to a unique value. Every element in the codomain are mapped to. Yep, that's
Okay,
correct.
and this is one-to-one correspondence.
Yeah, but I don't use the term one-to-one, because I think that's onto and all those terms, they're confusing to me. Injection, surjection, and bijection, they're more clear to me. Yep.
Yeah, and this is like, I think this is the only tiles computer science can do. They're called wing tiles,
Oh, Wang tile.
and you
Mhm.
do things like this.
So, okay. All right.
But
I did the late petition for this class. And,
Okay.
I'm not in the class yet.
I will double check to see if I have any application coming in, yeah.
Thank you.
Mhm.
Is there anything that I have to do or just wait for it?
No, I don't think so. Yeah, once the petition is filed, then I have to agree, approve, and then the dean has to do it too. Mhm. Alrighty.